And it actually goes both ways. There's a theorem. All right? Let me state the theorem for you. Well, here's some theorems. Number one, there exists basis beta such that the matrix of T with respect to the beta basis is diagonal. That's true if and only if there exists an eigenbasis beta for T. So diagonalizability of a linear transformation, and by that I mean that you can find a basis which makes the matrix for the transformation a diagonal matrix. Diagonalizability is tantamount to the existence of an eigenbasis. I'll just call that a theorem. The proof of this, all right? It's really not much different than the example we just went through. So if T of beta beta diagonal, what does that mean? For T. Sorry, my G has morphed into the T for T. This is all for T linear, you know? Right, linear map. Or linear transformation. So check it out. If that matrix is diagonal, what's that mean for the basis beta v1 through vn? That means that if we look at the matrix, what does it mean for the matrix to be diagonal? Think about it. It means that that's like some constant, right, times E1. Well, I'll write it this way. C1, C2, right? Which is to say C1, E1, C2, E2, right? Cn, En. Each column is a standard basis, right? But think back to what we meant by T beta beta. What's the jth column of that? Like Cj, Ej is equal to the coordinate vector of T of Vj with respect to the beta basis. Because this is the jth column of the matrix T beta beta, which we're assuming is diagonal, so it's a scalar multiple by the jth identity matrix, the jth standard basis, right? But what does that mean? This says, right? What if we take the inverse coordinate mapping on both sides of this? This means that T of Vj is equal to Cj Ej, Cj Vj rather, right? What does that mean? What does that make Vj? Now, this says that Vj is eigenvector with eigenvalue lambda j equal to, let's say, Cj. And since that holds for j equals to 1, 2, 3, all the way out to n, that means that this beta basis we're looking at is, in fact, nothing more than an eigenbasis. That's half of the proof of the theorem. the fact that the matrix is diagonal with respect to some basis means we can track back and see that every element of that basis is in fact an eigenvector for the map. And then, of course, the other direction is almost the same thing. If you have T of Vj equal to lambda j Vj for all j equals to 1, 2, n, then that implies that the matrix of T with respect to the beta basis is in fact equal to lambda 1, lambda 2, lambda n by the sort of calculations we've just been doing, which is to say that it's diagonal. All right? So existence of an eigenbasis if and only if the matrix is, if and only if the linear transformation is diagonalizable. I guess I should mention coordinate change. So like theorem, the T beta beta coordinate map, matrix, it's equal to the matrix times the standard matrix of T times the beta basis matrix. Again, this is how coordinate change works for a non-standard. If we have a non-standard basis for a linear transformation on RT, on Rn, then the matrix is a similarity transformation of the standard matrix. Do you guys know similarity transformation? Does this make any, have you never heard this before? Maybe not. I should throw this definition out for you. Definition, A similar to B if and only if there exists P in GLN-R such that B is equal to P inverse AP. In the case that happens, we say that A and B are similar matrices. So with that in mind, we can define what we mean by a matrix being diagonalizable. What does it mean for a matrix to be diagonalizable? Yeah?
So you're saying A times P and then P inverse times A?
P inverse AP?
Yeah.
That's not trivial because matrix multiplication does not commute. I can't just slide the P over there. Like that's...
Yeah, I remember that.
So A is diagonalizable if and only if A similar to diagonal matrix. And with the theorem I have on the board, we can say this: a matrix is diagonalizable if and only if it has an eigenbasis. And we can use that eigenbasis to actually perform the similarity transformation. All right? Now, there's much more to say about eigenvectors, all right? Let me just tell you some of the more important theorems about them. First of all, linear independence. So theorem, you know, if V1 and V2 are eigenvectors with lambda 1 not equal to lambda 2, then V1, V2 are linearly independent. So And this extends past 2. Like if I had n eigenvectors, which had n distinct eigenvalues, it would be then the case that those n eigenvectors were linearly independent. So distinct eigenvalues give you distinct eigenvectors. Okay? You can prove this. It's not that hard. Likewise for... So what does this mean? For example, if you have a matrix as an application, right? If A is in 3 by 3 matrix, right? With V1, V2, and V3, right? All non-zero, with lambda 1 equal to 1, lambda 2 equal to 2, lambda 3 equal to 3, all right? So suppose you have 3 by 3 matrix, you have 3 eigenvectors with 3 distinct eigenvalues, right? What does that mean? V1, V2, V3 is linearly independent, right? So you have a linearly independent subset of R3 with 3 vectors. What can you tell me about that? You guys tell me, what does it mean to have a linearly independent subset of R3 with 3 vectors in it? What can you say about that? Do they span R3? They span R3, and in fact, it's a linearly independent spanning set. It's what we would call a basis for R3, right? In other words, this is a eigenbasis, eigenbasis for A. What does that tell me? A is, in fact, diagonalizable, right? And even though I haven't told you what A is, or even what the vectors V1, V2, and V3 are, I can tell you how to do it. If you take V1, V2, V3, you concatenate them like so, invert that, multiply A in the middle, multiply V1, V2, V3 again over here, like this, that will work out to the diagonal matrix 1, 2, 3. That's the calculation. This is how it works. So to diagonalize a matrix, all I have to do is calculate the eigenvalues, find the eigenvectors, and do this similarity transformation, and there it is. Now, so, all right, so it can't be quite this nice, right? Like, what else is there? Well, we don't really need the what else there is there for O'Neill, all right? But I will just tell you that, so there's a general problem here you can ask, right? Given 2 matrices, right, are they similar to one another? So that's like a natural question to ask when you're thinking about these things, right? Question.
Are we defining similarity as the P inverse of P?
Right. Given A and B in Rn by n, when is A similar to B? Well, the definition is that there exists a P, an invertible n by n matrix P, such that B is P inverse AP, right? But when is that, given two matrices, when is it possible? When is it possible to find a P to show that they're similar? When is it not possible? This is an interesting question because basically what similarity is it's how we change the formula for a linear map. So if you change coordinates, right, then the formula for the linear map changes according to a similarity transformation. And as we've seen in an example that I erased up here, it could change it from something that was somewhat complicated, like, okay, so the original formula for example 4 was T of xy was, what was the matrix for example 4, guys, remind me? What was the matrix? It was 1, 2, 2, 1. Okay, so the original formula was x plus 2y, and then 2x plus y, right? That's the original formula for t. What's the formula look like in eigencoordinates? In eigencoordinates, x bar, y bar, the formula is literally minus x bar, comma, minus 3y bar. So the formula in eigencoordinates is very, very simple. This is cool. So if A and B are similar, what that means in a nutshell is that they can represent the same linear map. You could change coordinates and change the formula for A into the formula corresponding to B. So if we look at the set of all possible matrices, like all the matrices which are similar are representing essentially the same linear map, just up to a change of coordinates. So it's an interesting thing to consider. Is it like a push forward? You probably could look at it that way. I haven't thought of that.
Well, I mean,
Yeah.
that's essentially what it is, right? Because you're doing one map to another map.
Yeah, yeah. But anyway, to get you to the end of the story here without taking 2 weeks, the answer to this is ultimately given not actually by, so there are maps which are not diagonalizable. So we can't just use eigenvectors and eigenvalues, right? If two matrices have the same set of eigenvalues up to reordering, then maybe they're similar. It kind of still depends on the substructure of things. But the ultimate answer here is given by something called Jordan form. So I can talk to you guys more about that some other time, but I just wanted to tell you that the Jordan form is actually the thing you want to sort of measure similarity by. Given two matrices, if they have the same Jordan form up to a reordering of the blocks, they're similar. And so the Jordan form is the concept which generalizes this notion of diagonalizability to cover not just a special type of matrix, actually it covers all kinds of matrices. In the real case, you actually want to look at what's called the real Jordan form. The real Jordan form, it has pieces which correspond to the real eigenvalues, and then it has other pieces which correspond to the complex eigenvalues. Those complex eigenvalues have to do with rotation dilation blocks. That's the real Jordan form. But anyway, that's a good 3 weeks of math. All right, we actually don't need all that, thankfully. So, so distinct eigenvalues, great. And then there's, better yet, here's the theorem that we really need. All right, so here it goes. If A is equal to A transpose, and this is an n by n real matrix, okay? Suppose you have an n by n real matrix, all right? Then there exists an orthonormal eigenbasis with lambda 1, lambda 2, possibly repeated, right? Lambda n in the reals, such that, you know, a v1, a vj equals to lambda j vj for all j. Orthonormal eigenbasis, though, that means that if I take beta v1 Vn like that, then the matrix of beta times the matrix of beta transpose is the identity. These vectors are perpendicular, pairwise perpendicular, and they all have length 1. I constructed the orthonormal eigenbasis for the 1, 2, 2, 1 matrix. Actually, this is not just an if-then. This is actually an if and only if. So there exists an orthonormal eigenbasis for your matrix if and only if it's a symmetric real matrix. But hey, how much trouble is it to check if a matrix is symmetric? Like none, right? So, I mean, I think after some of the stuff we've done in here, it's a little bit scary, but this theorem, man, this is nice. So if we have a symmetric matrix, then there exists an orthonormal eigenbasis. So it says not only do the eigenvalues exist and they're real, you can choose the eigenvectors such that they're pairwise perpendicular and all have length 1. That's very nice. So here's an application. And so what that also means, let me just stop writing. What this also means is that if we have a symmetric, if we have a linear transformation, right, and it has a symmetric matrix, then that means that that matrix is diagonalizable, that that transformation is diagonalizable. And it's a little bit more than that. So let's see here if I can write this out. So if we have like t of x bar 1 v1 plus x bar 2 v2 plus x bar n vn. Suppose that you know, suppose t has orthonormal eigenbasis v1, vn with eigenvalues lambda 1 through lambda n. What's the formula for t look like? It's what? It's lambda 1 v1, right? Oh, idiot. Fine. So lambda 1, x bar 1, v1, lambda 2, x bar 2, v2, lambda n, x bar n, vn. I mean, and if you wanted to say things about the formula in, let's see here. Oh, like what's the furthest, if we restrict the inputs to have length 1 from the origin, how far can the outputs be? Like suppose that we're looking at, you know, inputs that have x bar 1 squared, x bar n squared equal to 1. So you could think about that, and you could figure out. I'm sorry, I'm getting too far off track here. Let me stop this. I mean, that's a formula, great. Let's see here. I'm trying to think of what else I need to tell you. I think the only other thing I can think of at the moment is there's 2 important formulas for eigenvalues that we should know about. So, fun formulas. And one of them involves the trace, and the other one involves the determinant. Okay, so the trace and the determinant. So first of all, do you guys know what the trace is? Yeah, the trace of the matrix A is the sum of the eigenvalues, actually. So the trace is the sum of the eigenvalues. All right. And the trace of a matrix is the sum of the diagonals. Okay? The trace is the sum of the diagonals. And the determinant of a matrix is the product of the eigenvalues. So those are useful to know about. So how about the this 1, 2, 2, 1 example we had? How'd that go? What's the trace there? The trace is 3. 1 plus 2 is 3. What were our eigenvalues? Oh, the trace is 2. Trace is 2. What were our eigenvalues? Negative 1 and 3. Minus 1 plus 3? 2. What's the product of our eigenvalues? Minus 1 times 3. Negative 3. What's the determinant? Not an accident. Not an accident. So these are general truths. Anyway, I'm going to stop here for a second.